Okay, in this video, let's look at problem 4. In problem 4, we have a Zener diode. Let me, and we've done Zener diode, but we've done it very quickly in class, isn't it? So a Zener diode in the forward bias behaves just like a normal diode, right? So if you draw the characteristics of a Zener diode and you plot the voltage across the Zener diode along and the current in the forward bias, it will just look like a normal diode. However, it's in the reverse bias that Zener diodes are more interesting, isn't it? Because it's the same as the diode to a certain level, and when it reaches the breakdown voltage, the characteristic goes like this. And Zener diodes, even though they break down, the breakdown is reversible, so it can go in and come back from the breakdown. Okay. Now let's say that the breakdown starts at this voltage. At this point, okay, let's say this is our measure of the breakdown. So this voltage is called the knee voltage, and this current is called the knee current. Okay, that's just the point at which we say that the breakdown is starting. Okay, so that's one thing. And another thing to remember is look at the slope here for the Zener diode. It looks like a resistor as far as in the breakdown it's concerned. It's almost like a straight line, right? And so you can replace the Zener diode in reverse bias with this kind of a model. So let me draw a Zener diode here. And you can replace this with a voltage and a resistance. Okay, so this, let's say this is called RZ, the resistance of the Zener diode. And this is, let's say, VZ0, which is the breakdown voltage of the uh, Zener diode. Okay, now knowing this, I think we can go to solve the problems that we are doing. So let's take a look at that in the next now. So in the first part of the question, you are asked to find out the output without any load and with V plus at its nominal value. So you can see that V plus here, let me use a blue color pen. So V plus here is 10 volts plus minus 1 volt. By nominal value, we just mean 10 volts, okay? Without this plus minus 1 volt. So when V plus is 10 volt, and I've not included the load resistance here, so that's the circuit. So what is the output voltage? What we've been given in the question is Vz equal to 6.8 volts at Iz equal to 5 milliamperes, right? And we've also been given that Rz equal to 20 ohms. So how would the model of the Zener diode look? So if we so the model of the Zener diode will look like this, isn't it? So it is some kind of voltage here and a resistance, and this resistance is Rz, which is equal to 20 ohms. This voltage is Vz0, which we have not yet calculated. Okay, and then we have been given this, we know that there is a resistance here in the circuit, R equal to 0.5 kilo ohms, and the voltage is 10 volts. So this is our circuit. Now how do we calculate Vz0? Now when Iz is equal to 5 milliamperes, so when 5 milliamperes flows through the Zener diode, right, when this Iz is equal to 5 milliamperes, what is the voltage at the output of the Zener going to be? It's going to be this Vz0 plus the drop across this resistance. And what's that equal to? That's equal to 6.8 volts. Okay, so let's do that. So what we are saying is 6.8 volts equal to Vz0 plus 20 times Iz. And you can, from here you can calculate the value of Vz0. We know what Iz is. Iz is 5 milliamperes. So if you calculate the value, you will get something like 6.7 volts. Okay, so now what we can do is, having done this, so now we know the value of Vz. So let me just take away these red markings because we were using to calculate the value of VZ0. So what does our circuit look like now? So we have this VZ0 equal to 6.7 volts, and we have RZ equal to 20 ohms. Okay, so now we need to solve that this circuit. Now we know that whatever current IR is there, the same current also flows like this IZ, because there is no load, right? IR and IZ are equal, which then means that what is the voltage VO then, right? VO, let's write in black. So VO is going to be equal to 6.7 plus IZ RZ. Okay. And what is IZ going to be? If you look at this block here, you can see that this is 10 volts, and then you have another drop of 6.7 volts, and then you have two resistors. So basically what IZ is going to become is IZ will be equal to 10 minus 6.7 divided by R plus RZ, which is going to be equal to 3.3 divided by 0.52, and that's going to be equal to 6.35 milliamperes. Now, having this IZ value, we can calculate VO. VO is then equal to 6.7 plus 6.35 milliamperes times 20, and that turns out to be equal to, let's see the value, 6.83 volts.